I invite you and encourage you not to fear that knowledge will do away with God, but rather to be open to the possibility that it may, in fact, deepen our understanding of Him. A dieter striving to lose a few pounds probably worries about the calories in the food he eats. But to a scientist, calories are the measure of all types of energy, not just the energy stored in food. In fact, scientists use energy as a tool with which to study nature, much as a doctor uses a stethoscope to study your heart and lungs. While most scientists use light energy to study the physical universe, heat or thermal energy can also be used to discover important properties of matter. Using heat energy has been an almost constant aspect of my scholarly work since 1974. Over the years, I have counted calories to study a wide range of problems: metabolic processes in E. coli and yeast cells, the stability of minerals found on Mars, of ceramics proposed for the storage of nuclear wastes, and of materials under development for batteries and hydrogen storage. While that list doesn't touch upon all the riddles of the universe, it does span scientific disciplines from biology and chemistry through solid-state physics and on to geology. Currently, I and my BYU colleague, chemistry professor Brian Woodfield, and our students, together with collaborators from other universities, are working to understand the nano-universe. We want to know what happens to the properties of materials when they exist as particles so small that it would take more than 20 million of them lined up side by side to make an inch. Some experiments show, and some theoretical models do predict, that such small particles can behave very differently from large chunks of the very same stuff. There is much hope that these differences can be exploited to create new technologies or new products. On a mundane level, for example, new, more efficient sunscreens have been developed using nanoparticles of zinc oxide. Many states and the federal government have created nano initiatives hoping to catch the nano wave. I'm going to describe today some of our experiments to study magnetism in those very small particles. I hope not to snow you with a lot of technical details, but rather to give you a flavor of what we learned from these studies. Some principles are easier to demonstrate with light energy, so I'm going to start first with a little illustration of how scientists use light to probe matter, and then we'll come back to heat energy. I have here 4 different colored LED flashlights, light-emitting diodes. I have ones that emit blue light, ones that emit green light, red light, and white light. Let's remember a few things about light. A light beam actually consists of many millions and millions of little particles that carry the energy. Scientists call those particles photons. The color of light is related to the energy of each bundle or each photon. A blue photon has more energy than does a green photon, and green photons have more energy than red photons. Remember from Newton's experiments with white light and the prism that white light is actually made up of all the colors of the rainbow put together. Well, science is about doing experiments and making observations, so let's do some. I have here 2 cylinders. One contains pure water, the other contains cranberry juice. I don't think you're going to have any trouble telling the difference. If I take the white light and pass it through the water cylinder, what you see is white light. Take the red light and pass it through the cylinder of water, I get red light coming out. The blue light coming out, and the green light coming out. The color that I start off with is what shows up when I pass the light through the cylinder containing water. Now let's look what happens when I do the same thing with the cranberry juice. If I take the white light and pass it through the cranberry juice, what I get is red light coming out. If I take the red light and pass it through the cranberry juice, what I get is red light coming out. When I take the green light and pass it through the cranberry juice, I don't get any light coming out at all. And if I do the same thing with the blue light I get the same result. As a scientist, I would talk about that as the blue light and the green light were being absorbed by the cranberry juice. To summarize, light passing through the water cylinder goes through exactly the way it came out of the flashlight. But as I pass light through the cranberry juice, red light passes through, but the blue light and the green light are absorbed. How can we understand the results of those experiments you just saw? Scientists, like artists, are very visual folks. We use diagrams and icons to represent our ideas. This diagram shown here represents two different states of matter. The arrow tells us that energy increases as you go from bottom to top. The upper state is higher in energy than the lower state. Now, matter has many different types of energy levels, but as shown in this diagram, the gaps between levels can be very large. Molecules can only absorb a photon, however, if the photon's energy exactly matches the energy difference between two levels. Let's add some water molecules to this picture. In the water-filled cylinder, all the molecules were in a low energy state, and despite the glitching oxygen atoms back there, these are in low energy states. Now, let's add some light. The wavy colored arrows in this diagram represent the different photons, and their heights indicate the relative energies of the photons. Notice that none of the photons have energies that match the states in water. The photons can't be swallowed up by the water because they don't match. Instead, they pass right through. We can apply the same reasoning and the same energy diagrams to cranberry juice. Since the molecules in the juice are pretty complicated, let's just use a few cranberries to represent them. Because the juice molecules absorbed blue and green photons, we can infer that they must have energy states that the water molecules don't have. And the gaps between levels must match the energies of the blue photons and the green photons. Red light passes right through the juice because there are no states in the molecules with the energy of red photons. Now, of course, the instruments of a modern scientist are far more sophisticated than those flashlights, but the principle is really the same. By shining light of different colors onto molecules and seeing what colors are absorbed, you can identify energy states in the molecule. Knowing what energy states are present helps you to deduce molecular structures. Explaining how scientists make the leap from energies to structures, however, would take the rest of my time. So come to the Benson building and take a chemistry class if you're interested. Just as light can be used to study energy levels in matter, so can thermal energy. Temperature is a measure of that kind of energy, just as color is a measure of light energy. Two demonstrations are going to illustrate what heat or thermal energy can tell us about different kinds of energy states in matter. Everyone knows that water boils at 212 degrees Fahrenheit when you're at sea level, and here in Utah, because of the altitude, it boils a little bit lower. Here in this vessel, I have a clear, bubbly liquid. Looks like boiling water, doesn't it? Well, let's do an experiment to see if it is boiling water. Everybody knows what happens when you cook broccoli in boiling water, so let's try cooking some broccoli. That's not what usually happens when I cook broccoli at home. Stops boiling, let's see. That also isn't what happens when you cook broccoli at home. This flask actually contains liquid nitrogen. Nitrogen as a gas is the major component of the air we breathe. Like steam, which is gaseous water, gaseous nitrogen can be condensed or converted back to liquid by cooling it down. Nitrogen has to be cooled all the way down to minus 321 degrees Fahrenheit to become liquid. That's 500 degrees lower than the boiling or condensation temperature of water. I didn't cook broccoli here. I froze it solid. Liquid water and liquid nitrogen both boil. Why does liquid nitrogen boil at such a lower temperature than water? All liquid molecules experience attractive forces that tend to keep the molecules close together. To boil, molecules must have enough energy to overcome those attractive forces, enabling them to break away and enter the gas state. The energy to do this comes in the form of heat, also known as thermal energy. The connection between thermal energy and temperature is given by a simple relationship. This is the only equation I'm going to show. Heat energy is equal to K sub B times temperature, where K sub B is a proportionality constant, and T is a temperature on the scientific or absolute scale. On the absolute scale, room temperature is about 300 degrees, and water boils at 373 degrees. According to this relationship, the low boiling temperature of nitrogen corresponds to a small amount of energy. The available heat energy is small, but it's sufficient to overcome the attractive forces between nitrogen molecules. Water, as indicated by its higher boiling temperature, needs much more energy to overcome its intermolecular interactions. The second demonstration shows a completely different kind of phenomenon, but one that is still controlled by thermal energy. This black circular disk is a superconductor material made of bismuth, strontium, calcium, copper, and oxygen. You can understand why they call it BSCCO for short. This little cube is a very strong magnet. Here in the liquid is our old friend, liquid nitrogen. The liquid nitrogen is a convenient way to cool the superconductor down to below about minus 262 degrees Fahrenheit, where some magic is going to take place. I'm going to put the magnet on top of another piece of superconducting material, and I'm going to pour some liquid nitrogen over the superconductor to make it cold. Watch the magnet very carefully and see what happens when the superconductor gets cold. Did you see the magnet jump up ever so gently? At that point, the temperature at which that magnet jumped up, the material, the BSCCO, got to a temperature of minus 261 degrees Fahrenheit and went into its superconducting state. Now, to prove to you that I don't have some invisible wires there holding that magnet up, let me get it spinning and prove to you that it's not being supported by anything other than the interaction of the magnet, the magnetic forces coming from the magnet, and essentially the reflection from that superconductor. When the superconductor disk warms up from its very low temperature put onto it by the liquid nitrogen, that is, when it gets to above minus 262 degrees Fahrenheit, the material goes back to its normal insulating state and the magnet falls back down. The levitation experiment is over. Exactly what causes the phenomenon of superconductivity in this material is not yet well understood. What we do know is that cooling the disk down transforms the electrons into a different state, one in which they flow with no electrical resistance. Above that minus 260 some degrees Fahrenheit, the electrons have too much thermal energy to occupy the superconducting state, and they behave like normal magnets, normal insulating material, Like the liquid-gas transformation, the temperature of the state change reflects the strength of the interaction responsible for the phenomenon. Let me repeat that point. It's probably the key take-home message so far. The temperature at which a phenomenon takes place measures the strength of the fundamental interactions that give rise to the phenomenon. Weak interactions reveal themselves at low temperatures, strong ones at high temperatures. For the last few years, my research group has been using heat energy to study magnetism. Now, I suspect everybody has played with magnets at one time or another, and you probably know that not all materials are magnetic. You just can't place a kitchen magnet on any surface and get it to stick. You probably also know that two magnets have to get to pretty close together before you feel a force between them. Well, let's take a peek at magnetism on the atomic level. To illustrate the key points, I'm going to take as my main example a material called cobalt oxide, because it is the substance we have studied most extensively. Cobalt oxide contains two types of atoms, cobalt and oxygen, shown here as blue and red balls respectively. The ions arrange themselves in the shape of a cube, with every cobalt ion surrounded by 6 oxygens and vice versa. Cobalt ions contain unpaired electrons. These unpaired electrons are the essential requirement for magnetism. All electrons have a property that we call spin, and I'll represent the spin by an arrow and locate it on the cobalt ions. Now remember, the arrow is just symbolic. If you look at a set of particles of cobalt oxide, you won't see a lot of arrows. The spins on different cobalt ions can interact with each other. Somewhat surprisingly, in oxide-containing minerals, the spin-spin interaction between magnetic ions takes place through the intervening oxygen atom rather than by direct ion-ion interactions. Because of the arrangement of ions, the interaction can extend indefinitely over the repeating cobalt-oxygen units. It is the collective behavior arising from long-range interactions among many spins that gives rise to the phenomenon we associate with magnetism. The strength of the interaction between the spins determines the temperature range over which the material is magnetic. When the energy of the interaction between the spins is stronger than the thermal energy, the spins line up in an orderly fashion. In cobalt oxide, the spins line up in an anti-parallel arrangement. But in iron or nickel, the spins line up in parallel orientations. It's what gives rise to their very strong magnetism. Ordered arrangements of spins is the situation at low temperatures. Eventually, however, as the temperature is raised, there is enough thermal energy to overcome the locked orientation of the spins, and the spins begin to flip, destroying the magnetic order. For iron, that temperature is about 1,300 degrees Fahrenheit, while for COO, it's about 60 degrees Fahrenheit, or pretty close to room temperature. Again, the temperature differences tell us that the interactions between spins on iron interact much more strongly than the spin interactions between cobalts. Does the development of neatly organized spins depend upon the size of the cobalt oxide particles? Is the coupling between spins stronger if the interaction can take place over many units? What if the particle isn't perfectly crystalline? What if one or more oxygen atoms are missing in the lattice, or some other kind of atom sits at the oxygen site? We have studied magnetic effects in cobalt oxide of 3 particle sizes to try and answer those questions. To help you grasp the range of particle sizes, I'm going to relate the sizes to some familiar distances. Our largest particles were big single crystals of about 1/4 inch in length. Let's set that size equal to the 1.8 miles that separate University Mall from the BYU football stadium. The middle-sized particles were powders with dimensions of about 50 microns. On the University Mall scale, these particles would have the dimensions of the length of a football field, 100 yards. Finally, I'm going to show you results of 2 sets of nanoparticles. On our Mall distance scale, those smallest particles would be about the size of the coin tossed at the recent Super Bowl game. As a native of southwestern Pennsylvania and a lifelong fan of the Steelers, I just couldn't resist the reference. Way to go, Steelers. Our studies of magnetism in cobalt oxide, ranging from large single crystals to fine powders to very, very small particles, probe distances that vary by a factor of about 1 million. Our experimental studies consist of cooling samples down to low temperatures, much below the temperature of liquid nitrogen, heating them back up in a controlled fashion, and measuring how many calories are needed to change the temperature. However, I'm actually going to show you results that are, mathematically speaking, the temperature derivative of the energy called the heat capacity. While I love the elegance and the theoretical and mathematical underpinnings that we bring to our analysis of results, I'm not going to introduce them to you here, just give you the highlights. Here's the first set of results. The heat capacity of our big crystals measured as a function of temperature near room temperature. Let's point out the important features. Heat capacity is plotted in the vertical direction, temperature given in absolute temperature units is on the horizontal direction. Starting from the low temperature side on the left, the heat capacity increases with increasing temperature. Then the heat capacity rises rapidly to a sharp point, and then even more suddenly it falls precipitously. Those features, gently increasing heat capacity, rapid escalation to a sharp point, and final sharp drop, and the temperature of the peak are the important bits of information we get from this curve. The shape of the heat capacity peak tells us how the magnetic order changes with temperature. At low temperatures, all the spins are locked into one orientation. As the thermal energy increases, a few spins break free and start to flip. That break makes it easier for a few other spins to uncouple, and the effect cascades rapidly. Well, what happens when the path length for magnetic interactions gets shorter, but not too short? The mid-sized particles, the powders, give us some idea. The red curve here presents the powder's heat capacity, while the blue curve is the big crystal data. Compare the key features for the two curves. The low temperature behavior is about the same, but the heat capacity in the transition region rises less steeply, it falls more slowly, and the peak appears at a slightly higher temperature. But overall, the magnetism hasn't changed drastically. Now, in this slide, the red curve gives the nanoparticle heat capacities, while the two blue curves present the previous results. For this sample, a fairly substantial change has taken place in the region around the transition temperature. What can we learn about these results? Well, remember, the peak shape indicates the length scale over which the interactions take place, and the peak temperature reveals the strength of the interactions between spins. The rise, sharp, and steep fall of the single crystal heat capacity say that the spin interactions extend for long distances within the crystal, and because the interactions break down over a very narrow temperature range, they must have similar energies. The broad peak from the nanoparticles tells us that the spin interactions extend over smaller distances and that the energy interaction is not uniform. We can also conclude that the average interaction energy in the nanoparticles is slightly less than the single crystals and powders because the peak temperature occurs at a slightly lower temperature. Any surprises from these results? Well, first, the studies of magnetism in other kinds of small particles have suggested that the magnetic effects can be completely destroyed at very small particle sizes. In cobalt oxide, while the peak shape has been diminished, magnetism is still clearly present. And secondly, when magnetism does persist in small particles, the transition temperature has usually been reported to be shifted to much lower temperatures, temperatures that are lower by as much as 200 degrees. Since the transition temperature measures interaction energy, that observation implies that there is much weaker spin interactions in nanoparticles. This is clearly not the case in cobalt oxide. A temperature shift of only a relatively few degrees is observed for those very large changes in particle size. So yes, our results do suggest that something a little different's going on here. To study this further, we did some more experiments using a new nanoparticle sample. Dr. Shengfang Liu, the postdoctoral fellow working with us, produced a beautiful new sample of nanoparticle cobalt oxide. Higher purity, more uniform particles, but essentially the same size as the first ones we studied. And that's a mean technical feat to do. But there is a surprising difference in the heat capacities. As before, the new red curve gives the new results, the new nanoparticle measurements, and the blue curves are data shown previously. The peak shape and the peak temperature from the new nanoparticles much more closely resembles the powders, which remember are bigger than a factor of 1,000 than the other nanoparticles. These new results were completely unexpected because they run counter to prevailing views on what happens at the small scale. It is the broad features in the first nanoparticles that are consistent with other measurements and predictions. Since the two sets of nanoparticles are essentially the same size, the difference cannot be a particle size effect. What are they due to? Our current hypothesis is that the original results reflect imperfections in the nanoparticles, Missing oxygen atoms, extra oxygen atoms, or even a misalignment of atomic layers can shorten path lengths and introduce a range of interaction energies. This hypothesis is supported by results obtained by a colleague of ours, Professor Francis Hellman at the University of California, Berkeley. Francis has found that thin films of cobalt oxide grown on magnesium oxide have a more perfect layer alignment than do cobalt oxide films grown on silicon dioxide, SiO2. Our two sets of nanoparticle heat capacities exactly parallel the results that Francis got on her films. Broad peaks at lower temperatures and the films with poor layer alignments, and sharp peaks at higher temperatures on the higher quality layers. Well, let me wrap up this part of my talk with these observations. Magnetism in cobalt oxide particles is quite robust. It survives with surprisingly little change, even when the particles undergo enormous changes in particle size. The high-quality results obtained on the new nano COO raise some questions for the nano world. Is cobalt oxide unusual? Or are some claims for particle size effects really just a manifestation of poor sample quality? If so, particle size effects would not be the first scientific phenomenon that turned out to be the result of impure samples and poor sample characterization. Even in physical processes, chemistry rules. I wished I had more time to describe other projects in which we use calories to study the nature of the universe. But in the few minutes remaining, I'd like to talk a little more philosophically. As a person who is both deeply committed to my faith and to my science, I am greatly troubled by the increasingly bitter and rapidly deepening chasm between certain people who identify themselves as being religious and other people who are scientists. The attacks come with vehemence from both sides. There are prominent scientists who view religious faith as mere superstition and discount religion as a source of understanding. On the other hand, some believers can be just as arrogant in their dismissal as scientists. For example, as legislative battles over the teaching of evolution continue, scientists are portrayed on the airwaves, in newsprint, and on blogs as evil destroyers of religious faith. In a recent neighborhood meeting with a local Utah politician, more than one participant claimed with absolute confidence that no one who believed in evolution could believe in God. It seems to me that a little humility is called for on both sides of this debate. As John Meekum wrote in a recent New York Times book review, light can neither enter into nor emanate from a closed mind. And intellectual humility, acknowledging what we do not and cannot know, is often the beginning of wisdom. As a high school student, I was introduced to the writings of Pierre Teilhard de Chardin, a Jesuit priest who was also a paleontologist. Teilhard was very possibly the first profoundly Christian thinker to attempt a reconciliation of evolution and Christianity. In his encyclical letter entitled Fides et Ratio, or Faith and Reason, Pope John Paul II says, faith tied to weak reason runs the grave risk of withering into myth or superstition, while reason, deprived of the knowledge gained from revelation, ultimately arrives at questions which it must acknowledge it cannot answer. The LDS apostle and member of a first presidency, Hugh B. Brown, writes in Vision and Valor, faith is the rock foundation of all religions, but there is no special virtue in blind faith. Here is the firm foundation for our religion, a religion that describes the glory of God as intelligence and proclaims that man is saved no faster than he gains knowledge. And Henry Eyring, a distinguished scientist and the father of your elder Eyring, says, the fundamental principle that has guided my religious life is that I need believe only what is true. The gospel is the truth as learned or discovered by whatever means and tools I can lay my hands on, or hand or mind on. So I am taken aback at the ferocity of those who would have you believe that it is impossible to believe in God and scientific evidence regarding origins of life. Those who vigorously deny findings of modern science remind me a bit of those who opposed Galileo. 400 years ago, Pope Urban VIII knew how God had organized the universe. Urban could not believe that God had arranged things the way Galileo's observations were finding them to be. But as we now know, God's universe turned out to be closer to that proposed by Galileo than the version demanded by Urban. Some advocates of intelligent design seem likewise to want to tell God that he couldn't or wouldn't have formed the universe the ways evolution and the Big Bang suggest it might have. I don't claim to know whether every aspect of life can be achieved by processes governed by random events. I do, however, know that predictable, orderly outcomes are possible in the physical universe when a very large number of random events are allowed to take place. For this reason, I don't want to be telling God he couldn't have used principles that he might yet allow us to discover. While refraining from telling God how he did things, I must admit to being more thrilled than frightened by what 21st century science seems to reveal about God. Paraphrasing slightly the words of Father George Coyne, the director of the Vatican Observatory and a Jesuit priest with a PhD in astronomy, modern science gives us a God who created a dynamic universe, a universe that itself participates in the very creativity that is God. And so I invite you and encourage you not to fear that knowledge will do away with God, but rather to be open to the possibility that it may, in fact, deepen our understanding of him. Because this lecture is an award address as well as a forum, I get to thank those who have brought me to this day. My students are, of course, the ones who've actually made all of the measurements that I've talked about today. I can't acknowledge enough their willingness to spend long, tedious hours to collect the experimental results. My BYU colleague, Brian Woodfield, shown here in the center, was my first graduate student and is now my collaborator. The collaboration is a great example of synergy because together we do better science than either of us could do alone. My parents and my own teachers and professors gave unstintingly of their time and energy to me as I was growing up. Their examples serve as my models, both as a parent and a teacher. My husband, Steve, and my two children, Sarah and JD, are the lights of my life. The National Science Foundation regularly ponders what is essential for women to succeed in science, and I know the answer. They need a husband like Steve who is willing to share the sacrifices as well as the joys that are part of raising families. And they need children like Sarah, shown here with her new husband, Jesse Christofferson, and JD, who get a kick out of a mom who can make liquid nitrogen ice cream for dessert. I also want to thank two people who were responsible for my coming to BYU in the first place. President and now Elder Jeffrey Holland and his provost and academic vice president, Jay Balleth, took a risk hiring that naive young Gentile fresh out of a postdoc without a long track record. And yet, from my first university conference, in which the theme was, "Unto whom much is given, much is expected," I knew that I'd made the right decision to come here. The Holland administration fostered an environment where I could indulge in my passion for both doing science and teaching science, as well as to service to something beyond myself. The Lee, Bateman, and Samuel administrations have each added their own dimensions to my experience here, but I say with fondness that I will regard those early years as a golden time in my life at BYU. To my colleagues and friends, the faculty and staff at BYU, including many who have now retired. Through way too many committee assignments, I have come to know of your commitments to this university, to its students, and to its sponsoring church. Your witness to your faith and your openness to mine have been blessings in my life. I thank you for your friendship. And for the dedication that you bring to your positions here, I salute you. to the members of my own faith community, to the members of St. Francis Catholic Church, for whom all creatures of our God and King resonates with special significance because the words are ultimately from our patron saint, St. Francis, to the members of the Catholic Diocese of Salt Lake who allowed me to participate at various levels and for whom their witnesses to our faith is a strong support to me, I thank you. And because I don't want to offend anyone, I hope I haven't, I want to close with these words of Pope John the 23rd. In essentials, unity. In doubtful matters, liberty. In all things, charity. And I say these things to you in the name of the Father, and of the Son, and of the Holy Spirit. Amen.